Yes, right now, yeah.
I should be spare.
Yeah. No, no, I will read this. शांति one copy is fine. One of सर मैं दे रहा हूँ आपको.
Ready?
हाँ.
Good afternoon, everyone. Welcome to the new session. I request Professor Suman Mehendia Madam to chair this session.
Thank you, organizers, for giving me the opportunity to chair the session. And for this session, we have the first talk from Professor M. Arivandan from AU Chennai. So I request the sir. So please. The talk will be of 25 plus 5.
So we have our first speaker, Professor M. Arivandan, on the topic enhancing the thermoelectric properties of nanostructure Gs for energy harvesting from waste to heat. Welcome, sir.
Thank you, Chair, for introducing me. And I'd like to thank Professor Anurag for inviting me to give a talk in this CANDEE 2023. And it's my pleasure to visit this campus and great event and well organized. And today I'm going to talk about the enhancing the thermoelectric properties of nanostructure, the germanium selenide for energy harvesting applications. As you know, the thermoelectrics is yeah, so it's okay. So as you know, the thermoelectrics is one of the very old technology actually. The based on Seebeck and Peltier effect, there are a lot of thermoelectric energy converters and thermoelectric coolers are there. a lot of research activities are going on in that. But after the evolution of nanoscience and technology, the interest on this thermoelectrics has emerged a lot. And because the thermoelectrics is one of the technology, by using that you can convert the thermal energy which are coming out from different industrial sources like thermal power plant or factories or automobiles, and those energies can be converted into the electrical energy because because that is one of the statistics given by research group at ACE Japan, and they said that more than 50% of this waste heat coming out from these industries have become waste and coming through the atmosphere, and they are creating a lot of pollutions and all, right? This thermoelectric technology is one of the potential technology to convert these waste heat into the electrical energy. And this is a typical thermoelectric device, and this kind of device and arrays of these devices can convert these kind of thermal energy into the electrical energy. And in that aspect, this technology can contribute in both aspects of controlling the environmental pollutions as well as for fulfilling the increase in energy demand. Right? So a typical thermoelectric device looks like, and it contains two thermoelectric legs, like P-type semiconductor and N-type semiconductor. And the thermal energy here is acting as a driving force to drive the charges from the hot end to the cold end of the respective semiconductors, and thereby we have the potential at the cold end, and that can be used to run the node. This is the mechanism how the thermoelectric device can convert the waste heat or thermal energy into electrical energy. But the situation is not so favorable and not so good compared to the kind of well-established energy conversion technologies like silicon photovoltaic and all. And this is the conversion efficiency, which is theoretically calculated from the relation, the input energy and output power. And this energy has been converted, calculated based on two factors. One is the hot end temperature of a thermoelectric device, and another one is that the ZT of the material. And look at that, this is the data, the theoretically calculated data. I just drawn one more dotted line, which is parallel to the x-axis. And this is the typical conversion efficiency of a silicon solar cell at the industrial scale. So if you want to increase the efficiency up to this level, then your material should withstand up to 1200 Kelvin, right? But at the same time, there are a lot of materials are available. Maybe I'll show some of the materials, but the one with the silicon germanium can withstand more than 1000 Kelvin. The rest of them can be stable only less than 1000 Kelvin. And because of that, you have to realize this high efficiency by tuning the figure of merit, that is a material-based parameter, and you can achieve the same efficiency even about half of that temperature, around 600 Kelvin. But for that, your ZT should be more than 2. So you have to tune the ZT of the material and how to tune the ZT of the material. So here, the nanotechnology playing a role, and this is the strategy that people are trying to follow, either by improving, this is the ZT. Actually, the ZT is the ratio between the power factor and thermal conductivity. The power factor is nothing but the square of Seebeck coefficient of electrical conductivity. So if you want to increase the ZT, either you have to increase the electrical conductivity or you have to decrease the thermal conductivity. But both are challenging tasks because they are quite interrelated. According to the Wetton transfer, they are quite the part of the electrical thermal conductivity is left to the electrical conductivity. So it is quite difficult to control independently, right? And whereas that this kind of relation is quite valid for metallic systems, but when you go for the semiconductor systems, the lattice part of thermal conductivity is quite dominant, and where you can play the phonon mean-free path there by nanostructuring the material, and these are all the typical nanostructured bulk material when you kind of compose this kind of material which contains a lot of defects like intentionally introduced defects like grind boundaries or lattice discrete or point defects. So these kind of defects act as a scattering centers for phonon, and those scattering centers affect the mean-free path, and that way you can control the lattice part of thermal conductivity, and that will lead to the ZT of the material, right? And another aspect is that with doping engineering, you can do a lot of doping, and you can vary the dopant concentrations. By doing that, you can increase the power factor. Okay? So these are the two strategies that people are trying to follow to improve the ZT of the material. Okay? And these are all the fundamental relations between the thermoelectric parameters for different kind of materials. And look at that, the Seebeck coefficient is quite high for the insulators and quite low for the metallic materials, since it is based on the carrier density according to the mode relations. And these are all the thermal conductivity, which contains two components, as I said in the beginning. And look at that, the electronic part of thermal conductivity is quite related to the electrical conductivity, but it is not at all related with the lattice thermal conductivity. Okay? So these are the approaches that people are trying to follow to improve the thermoelectric performance of the different material. The one thing is that they're reducing the thermal conductivity without degrading the electrical conductivity. And that can be possible by doing this kind of nano inclusion or nano defect engineering to improve this scattering process so that you can able to control the lattice part of thermal conductivity. And the nanostructuring of the material will help to tune the DOS of the system so that you can independently control the Seebeck as well as the electrical conductivity of the systems. And finally, the energy filtering effect, where you can able to have the multiple kind of interfaces, and there you can have the carrier selectivity so that you can able to improve the Seebeck coefficient through this kind of filtering effect. So the ultimate aim of the thermoelectric researchers is to find a kind of phonon glass and electron crystal where you can have the the reasonable decoupling of electron transport and ion transport. And these are some of that kind of systems like high TC superconductors are a kind of the atomic layers or kind of maybe electromobility layers, are kind of high entropy systems where you can able to have the high electron transport in the layered systems. And when you have the complex system where you can able to have the high low thermal conductivity like that. And the final objective of the research is to make this kind of thermoelectric device. For that, you need to have the N-type and P-type semiconductors, and one has to optimize the transport characteristics of both semiconductors. And then we can go for this kind of thermoelectric modules by combining the N-type and P-type in the group of systems. The basic requirement for this thermoelectric device is that we have to maintain the temperature gradient as cheap as possible. So as long as you have the temperature gradient between this hot end and cold end, then somehow you can able to draw the power from the hot end to the cold end, and that can be used to run the probe. Okay? And this is the overall the evolution of different kind of materials as the different group of materials, starting from the canthrates to the fuselars and to the chalcogenides, and of course recently the oxides. So the evolutions are like that. The cost of these systems are going down as we go for the earth abundant materials, and the cost effectiveness is increasing when you choose the proper low cost materials. And this is the reduce the thermal conductivity. As a function of that, you can able to improve the ZT of the material. Okay, and like that, there are two examples for the superlattices of selenites and tellurides. And these are all the materials which are available in the literatures, and some of them are commercially available, like bismuth telluride for low temperature applications and silicon germanium for high temperature applications. And these kind of materials are quite promising for high temperatures, as well as they can able to make it as a P-type as well as N-type systems. And the selenide is recently evolved as an intermediate temperature material like tin selenide. It shows the ZT of more than 2.5. So, and of course, silicon germanium for high temperature. And like that, the scenario of this, the thermoelectric research goes on this, the nanostructuring material, especially the semiconductor material, and trying to improve the transport characteristics. And we are also working on different kinds of semiconductors like the germanium selenides and tin selenides and some kind of oxides as well. And this is just I want to share some of our activities on this germanium selenide. And this is the work done by one of my students, Dr. Siddharth, and now he is at the Academia Sinica, Taiwan, and he is continuing the same kind of research. And he has prepared this germanium selenide by substituting tellurium at the selenium site, and just they have prepared the sample by the ball milling, and they have taken the samples with the stoichiometric ratio, and they have milled it with the optimized sample to ball ratios. And this will be after that they have calcinated the sample under hydrogen ambient about 400 degrees Celsius. And these are structural features of that the tin tellurium substituted germanium selenide. And look at that, this is structural features, and the tellurium is completely substituted at the selenium side up to 10% of the tellurium. And when the tellurium content is more than 10%, there is secondary phase formation of germanium telluride was observed. So that kind of, the structural variations are observed as a function of tellurium substitutions in the germanium selenide. And the morphological features tells about the nanostructuring of the samples, and the grains are highly interconnected. And these kind of interconnected grains will help for facilitating the electron transport in this kind of systems. And the tellurium incorporations in the systems are confirmed by using this kind of excuse analysis that tellurium is completely substituted in the systems, and the binding states of the rest of the elements are confirmed. And this is the transport characteristics of the tellurium substituted germanium selenide. And look at that, the pure systems are relatively high resistive, and when the tellurium content increases in the system, the resistance is quite decreasing, and up to several orders. Right? So it was there in the order of hundreds in a pure system, and when the tellurium is substituted in the system, the resistivity is decreased up to 3 orders. Then this is a variation between the carrier density and the mobility. Again, the mobility is dropping at the high carrier density systems because of this scattering process. And the Seebeck coefficient of this sample, which is compacted by the hydraulic press, was measured by the Seebeck measurement systems. And the Seebeck coefficient is quite high for the pure system because of its high resistive nature. But whereas, when the tellurium content increases, the Seebeck coefficient is decreasing as a function of tellurium content because of the variation in the resistivity of the sample. And this is the relation between the Seebeck coefficient and the carrier density, and that obeys the modulations as they are inversely proportional to each other, and that gives the reliability of the measured data. And the variations of the Seebeck coefficient is accordance with the resistivity variations. And based on the measured resistance and the Seebeck coefficient, the power factor has been calculated. And the power factor is quite high for the tellurium substituted sample compared to the 20% tellurium substituted sample compared to the pure systems. Okay? And then the thermal conductivity of the system has been measured for the tellurium substituted as well as the pure systems. And look at that, compared to the pure system, the tellurium substituted system shows relatively low thermal conductivity, especially for the 10% substituted one. But it's slightly increasing when the tellurium content is more. So the scattering mechanism is the responsible factor for this kind of variation in the thermal conductivity. And the tellurium substitution increases the unharmonicity of phonon vibration in the system. And because of that, the thermal conductivity is varied in the tellurium substituted sample compared to the pure systems. And based on these variations, we just measured the, again, it's okay, it's okay. Okay, so this is the ZT, the figure of merit of this tellurium substituted tin selenide, and the 20% tellurium substituted sample shows relatively high figure of merit compared to the rest of the sample, and that is also quite relatively higher than that of the reported similar kind of systems. So this kind of work shows that the substitution of tellurium is quite beneficial for improving the performance of the systems. And similarly, we just tried the copper substitution at the germanium site instead of selenium site. And there we just prepared the sample with this hydrogen decryptation method, and we just prepared the sample with different copper content, and these are all the synthesized sample after the hydrogen decryptation, and then pelletized into this 3D nanostructural materials. And these kind of pellets were used to measure all these kind of transport characteristics. And this is structural features, but this kind of structural features, the system behaves quite differently. That means, the secondary phases are quite dominant, and the secondary phases of copper-rich secondary phases were observed compared to the tellurium substitution at the selenium site, because the tellurium substitution is quite favorable, and the solid solubility of tellurium in germanium selenide is quite higher. But whereas when we substitute the copper with the germanium selenide, the secondary phases were formed, and especially the secondary phases of copper-rich secondary phases are observed in the system. So the system contains a lot of mixed phases, and of course the grinds are highly interconnected, and we have the highly compact structure of this copper substituted germanium selenide. And this is the transport characteristics. The resistivity is quite high for the pure systems, and the resistivity has been decreased when the copper content increases in the system, and the carrier concentration is increasing as a function of copper content, and because of that, the resistivity has been decreased. And the Seebeck coefficient is quite decreased compared to the pure system because of their low resistive nature, and the copper substitution in the systems and the formation of copper-rich phases are responsible for this kind of drastic variation in the Seebeck as well as the resistivity. And this is a power factor based on the Seebeck and resistivity, and the 20% of the here is 40% of copper substitution leads to improve the power factor compared to the rest of the systems. So that shows that the drastic improvement in the power factor because of the formation of copper-rich phases in this system. And the thermal conductivity of this copper-rich germanium selenide has been measured as a function of temperature. And look at that, the thermal conductivity is not so decreased. In contrast, the thermal conductivity has been increased when the copper substitutions are more. And this kind of, the high thermal conductivities are mainly based on this copper substitution, because these are all high conducting systems, so that the thermal conductivity has been increased in the system. And the ZT of the copper substituted sample shows relatively higher than that of the pure systems, as well as this kind of copper substitution is not helping for what we call the controlling the thermal conductivity, but it is helping for improving the power factor. And based on that, the ZT has been increased for this kind of copper substituted germanium selenide. And yeah, that's all about the content of this lecture, and we will take your questions. And these are all the summary of my talk. And these are all the funding agencies and my collaborators in Japan. And thank you.
Thank you, Professor, for completing the talk well in time. So we have a few questions. Yes, ma'am, please.
Yes. So page slide number 22. Can you just go back? First, you can stop at 29 also. So here, why this huge sudden change?
Yeah, this is because of that variation in the Seebeck as well as
So
the
then
resistivity.
the question is why that is kind of a sudden change?
Yeah, because the resistivity is drastically reduced. Look at the resistivity. The resistivity is there in the order of 10 ohms, say, and here for the 40% copper substituted, it is in the order of 10 to the power of -3. So this order of variation, nearly 4 order of variation of resistivity leads to variation in this power factor.
And then 22. Yeah, here you said that improvement, but keeping in mind the experiment, you said that the red ones are experimental data.
Yeah,
Red, yeah, pink.
that's from literature of a different system.
That is
The literature from different systems.
I know, but that is experimental.
Yeah, experiment.
So then I don't see the differences are so much. So can you call it improvement?
Yeah, but it's especially at high temperature there is a slight variation. But compared to that, at low temperature there is also improvement. But at high temperature there is a reasonable improvement. Yeah, but we need actually more data to confirm that. But the relatively higher than that of this one. But the variation, I agree with you. The variation is not so much.
Experimental, but inaccuracies or error.
Yeah, of course.
And another question is that you said that there was a try to decouple the Seebeck and the sigma. So how exactly that can be done?
Yeah, that can be done by modulating the device. When you nanostructure the material, based on the confinement, you can able to improve the device on certain energy level, and where
Affect your sigma also, no? Which if you have a density at EF, if your density of states varies a lot, then it should affect your conductivity.
Yeah, it will affect.
How you can decouple? That is a question, but anyway, it's okay.
Yeah. But there are some computational data for that in the quantum well structure where you can able to improve the form factor, especially by enhancing the CPET. And the CPET has been enhanced by modulating the effective mass, and the effective mass has a relation with the DOS. And this DOS modulation will help for improving the effective mass. And since the effective mass is directly related to the CPET, that is helping for increasing the CPET without much variation in the sigma.
Yes.
This is in the experimental part. I'm thinking about this ball milling process, which we also have used. What we found is that if you go for prolonged ball milling, especially for soft materials, there is a contamination of tungsten. So, haven't you got any kind of contamination? Have you observed something?
We didn't observe because we just optimized the condition first, and then we did the dry milling. A dry milling in a kind of solvent, high viscous solvent like toluene, and after that we treated it under high dynamic at a high temperature, where you can the defiltrate the sample and the formation are formations are more with pure phase compared to the
And the total time which has been used for this 300 RPM rotation, which, like duration.
Yeah, that depends
Duration
on the
dependent
depends on the system. Depends on the system. Normally, it will be about 24 hours to 48 hours.
When we go for such prolonged experiments, I found that there is a contamination of tungsten.
Yes, ma'am. That you have to optimize and you have to choose the proper ball and proper wire and proper sample and like that. And you should not mix it with the different systems. So for one system and one
But the
wire.
samples were characterized properly and there is no contamination.
Yeah, no contaminated phases. No.
Yes, there is a one query.
Yeah.
Like fundamental, maybe I am not explained.
Yeah, please.
But the thing is, silicon has the band gap of infrared medium, and it has some nanostructured silicon. We have seen that density is very good, like porous silicon and others. So, as silicon is very abundant, so why we choose that silicon germanium? Alloy, germanium and tin, so that is
Yeah, we are working on silicon germanium as well. Because the silicon germanium is one of the high temperature thermoelectric materials, and we have prepared the silicon germanium with the homogeneous compositions, and we have measured the thermoelectric characteristics of silicon germanium for a different composition. And silicon A70, germanium 30, to silicon 80, germanium 30 is the optimum concentrated composition for high thermoelectric performance. And this silicon germanium is one of the well-studied and well-established thermoelectric material, especially for high temperature application. But why we are working on this material? This is compared to silicon germanium and other chalcogenide semiconductor. This germanium selenide is quite the rarely studied or limited literature are there, and we need to understand more about the material property. So we just tried with different combinations.
Okay. Last query.
I have a concern about slide number 18 and 20. These two. In this slide, all above data curves are decreasing with showing the conversion, but the below one is getting increased and then very saturated. Last one.
For
Here?
germanium selenide, right?
Here?
Yeah. This behaving having a more trend than other ones.
It is showing
The trend with respect to temperature.
Yes.
Now, what's your question?
So, all above 4 trends are decreasing.
that result
Uh-huh.
only decreases with the difference.
Okay. Yeah. I understand because I feel that when the tellurium content is more, the systems behave relatively metallic, so that the resistivity is slightly increasing when the temperature is.
So for further concern and discussion can be continued during the lunch. Okay. So it's time for appreciation for the professor.
Thank you.
Therefore, kindly request our honorable chair, session chair to present this memento to our honorable speaker. Kindly accept this token from our side, sir.
Thank you.
I request our session chair to kindly announce our next speaker.
For the next talk of the session, I request Dr. Ram Ashish Chowdhury sir. And before starting the talk, I request Savita to just give the brief introduction about himself.
Mr. Ramaji Chowdhury, please come, welcome on the stage. He is a Joint Director DBFA at DRDO Headquarters, Ministry of Defence, Government of India. And he is going to speak before us on the topic SNT and the TD Project Management of SSPL DRDO. Welcome, sir.
मेरे भारत देश की विद्वत परिषद के सदस्यों, भारत के परिवार के सदस्यों, मैं अपने आप को बहुत गौरवान्वित महसूस कर रहा हूं कि मैं इस प्रदेश का निवासी हूं। मैं पनागर जबलपुर संस्कार धानी मध्य प्रदेश का रहने वाला हूं। मेरी शिक्षा सरकारी स्कूल में सीनियर बेसिक शाला से प्रारंभ होकर के उच्च शिक्षा के लिए सेंट अलाइसिस महाविद्यालय जबलपुर में ग्रेजुएशन किया। पोस्ट ग्रेजुएशन रानी दुर्गावती विश्वविद्यालय जबलपुर से प्राप्त किया। उसके पश्चात 5 साल बेरोजगार, लेकिन मैं खाली नहीं बैठा। मैंने 100 रुपए की भी नौकरी की, 1000 रुपए की भी नौकरी की, 2400 रुपए की नौकरी की, और जहां पे भी गया अपना सिग्नेचर छोड़ के आया। आज मेरी किस्मत है, मेरा काम है, आज सारे ऑनलाइन है मेरे साथ। पहली क्लास की टीचर भी ऑनलाइन है। मेरे वर्तमान कार्य क्षेत्र के मैं वर्तमान में जो मेरा परिचय दिया गया, पता नहीं कहां से डाउनलोड करके निकाला गया, जो फोटो लगी जब मैंने डीआरडीओ में अप्लाई किया था वो फोटो है। वर्तमान में मैं सॉलिड स्टेट फिजिक्स लैब में वैज्ञानिक गैप हूँ और रिकॉर्ड मैनेजमेंट के लिए प्रयोगशाला से नॉमिनेटेड रिकॉर्ड ऑफिसर हूँ और लैब में डिविजनल ऑफिसर तकनीकी सचिव हूँ। ये वर्तमान में रक्षा अनुसंधान का मुख्यालय, ये हमारी प्रयोगशाला का भवन है, मुख्य भवन है। जब मैंने ज्वाइन किया था तब जो साइंटिफिक एडवाइजर थे कलाम साहब थे, और 2019 में मेरे जबलपुर विश्वविद्यालय के प्राध्यापक ने 23 साल के बाद, 23 नहीं 19 और 25 साल के बाद खोज करके मेरा मोबाइल नंबर निकाला और मुझे आमंत्रित करके ये छोटा सा सम्मान, बहुत बड़ा सम्मान दिया जिसके काबिल। नेक्स्ट, मेरा एजुकेशन के बारे में बोल चुका हूँ। सेंट अलाइसिस महाविद्यालय में छात्र संघ का अध्यक्ष रहा हूँ। जब आरक्षण का मुद्दा चल रहा था तब इलेक्शन बंद कर दिए गए थे और मार्च के बेसिस पे मुझे मजबूरी में प्रेसिडेंट बनाया। वहां पर मैंने अपने प्रेसिडेंट का पद बहुत ही जिम्मेदारी से निभाया। एमएससी रानी दुर्गावती विश्वविद्यालय में फिजिक्स से की। वहां पर सॉलिड स्टेट फिजिक्स में 73.16% अंक प्राप्त करके सॉलिड स्टेट फिजिक्स में प्रथम स्थान प्राप्त किया। इसके पश्चात सेंट अलाइसिस महाविद्यालय में एक प्राध्यापक थे जो मेरी जिंदगी का टर्निंग पॉइंट थे, डॉक्टर कलवल दास, जिसमें बहुत लोग जानते होंगे उनको। आज मैं उनके घर गया हूं, टर्निंग पॉइंट में सर डॉक्टर चंद्रशेखर ऐसा प्लेटफॉर्म मेरे को जिंदगी में मिला होगा कि ना मिलेगा। वर्तमान में जहाँ कार्य कर रहा हूँ वहाँ के मेंटर, वहाँ के डायरेक्टर, एक्स डायरेक्टर नेक्स्ट स्लाइड। मैं अपने आप में इतना स्ट्रेस महसूस कर रहा था, ये बोल करके रिलैक्स कर रहा हूँ। एक टर्निंग पॉइंट और है, जब मैं शिक्षा ग्रहण कर रहा था, एक पन्ना के सर थे श्री एस.के. खरे, उन्होंने मेरे को गणित और भौतिक शास्त्र पढ़ाया। मेरी शक्ति मेरे धर्मगुरु, राष्ट्रपति पुरस्कार प्राप्त शिक्षक मेरे नाना जी, मेरे पिता, मेरी माँ। नेक्स्ट स्लाइड। वर्तमान में जहां कार्य कर रहा हूं वहां के रक्षा मंत्रालय, ये सारा जानकारी वेबसाइट में है, मेरा कोई कंट्रीब्यूशन नहीं है। वर्तमान साइंटिफिक एडवाइजर। नेक्स्ट स्लाइड। नेक्स्ट स्लाइड। ये स्ट्रक्चर है डीआरडीओ का। नेक्स्ट स्लाइड। नेक्स्ट स्लाइड। डीआरडीओ का नेक्स्ट स्लाइड। ये विजन एंड मिशन है, ये सब वेबसाइट पे। नेक्स्ट स्लाइड। हमारे 13 डीजी हैं, कारपोरेट डीजी, एक ब्रह्मोस के डीजी और 5 जो है वो कारपोरेट डीजी। ये डीजी टेक्निकल है। मैं इस समय जो कार्य कर रहा हूँ वो डॉक्टर सुमा वर्गीस डीएस एंड डायरेक्टर जनरल मैरिन कॉस हैं, और बाकी के 5 डीजी हैं। टोटल टेक्निकल 7 डीजी हैं। नेक्स्ट स्लाइड। ये कारपोरेट डायरेक्टरेट है, 5 कारपोरेट डायरेक्टरेट है और एक डीजी ब्रह्मोस है, टोटल 13 डीजी। नेक्स्ट स्लाइड। कारपोरेट डायरेक्टरेट्स में एक इंपॉर्टेंट जिसके बारे में बोलूंगा, ईआर एंड आईपीआर की डायरेक्टरेट। नेक्स्ट स्लाइड। नेक्स्ट स्लाइड। ये वर्किंग एरिया सारा वेबसाइट पे। नेक्स्ट स्लाइड। फास्ट, कम फास्ट। नेक्स्ट स्लाइड। नेक्स्ट, 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 नेक्स्ट। ये सारा डीआरडीओ का लाइफ साइंस, ये देख करके आप इसमें अपना एरिया डिसाइड। नेक्स्ट। नेवल सिस्टम। नेक्स्ट। सॉलिड स्टेट फिजिक्स जो लैब है उसका विजन और मिशन लिखा हुआ, आप वेबसाइट पे देख सकते हैं, डीआरडीओ की वेबसाइट से। और नेक्स्ट। एसएसपीएल कैसे बनी। नेक्स्ट। एरिया ऑफ वर्क। नेक्स्ट। सेंसर, क्रायोजेनिक, फ्यूचरिस्टिक। नेक्स्ट। ये एसएसपीएल के प्रोडक्ट हैं। एसएसपीएल का जो तकनीकी बनाई जाती है सेमीकंडक्टर और भी डिफरेंट फील्ड में, उनके प्रोडक्ट हैं। नेक्स्ट। एमएमआईसी वगैरह के जो प्रोडक्ट। नेक्स्ट। नेक्स्ट, नेक्स्ट, नेक्स्ट। फैसिलिटी अवेलेबल है, क्रिस्टल ग्रोथ, चेक्राल्स्की टेक्निक, ब्रिजमैन, एपिटेक्सियल ग्रोथ। एपिटेक्सी के बारे में आपको मणि मित्तल जी बताएंगे, मास्टर है ये, इन्होंने, इनका भी सफर बहुत लंबा रहा। नेक्स्ट। कैरेक्टराइजेशन फैसिलिटी, डीआरडीओ की लैब में इंटरेक्शन का एकेडमिया के साथ, पब्लिक सेक्टर के साथ, नेशनल लेबोरेटरी है डीआरडीओ की लैब। नेक्स्ट। आपको अगर कांटेक्ट करना है तो मेरी बजाय डायरेक्टर से कांटेक्ट करिए, वर्तमान डायरेक्टर। नेक्स्ट। ये चित्र आप देख रहे हैं, इसमें पहचानिए कौन है, इनको जानते हैं? कोई बताइए कौन है? ये मोदी जी कहाँ है यार? नहीं, सेकेंड वन। हाँ, इसरो सुना है नाम? आर्यभट्ट लॉन्च हुआ था, सुना है? कोस्टा साहब है, डॉक्टर एसपी कोस्टा, प्रोग्राम डायरेक्टर आर्यभट्ट, जबलपुर के थे, बाद में संत बन गए, श्री राम इंस्टीट्यूट के डायरेक्टर, श्री राम इंस्टीट्यूट के इंजीनियरिंग कॉलेज है। उसके बगल में जो खड़े हुए हैं ये मेरे गांव के पास के गांव के प्रोफेसर हैं, रानी दुर्गावती विश्वविद्यालय में टेक्निकल ऑफिसर। उसके बगल में मेरा दोस्त खड़ा है और इस साइड में खड़ा हूँ, ये उनके गांव का फोटो है। नेक्स्ट स्लाइड। अब मैं थोड़ा सा ग्रांट इन एड से आप क्या ले सकते हैं वो बता रहा हूँ। ग्रांट इन एड स्कीम है डीआरडीओ की। नेक्स्ट स्लाइड। अब मैं यहाँ पे इसके बारे में बताऊंगा। नेक्स्ट स्लाइड। ये कॉन्टेक्ट नंबर है बस। डीआरडीओ की जो ग्रांट इन एड स्कीम है, ईआर एंड आईपीआर के थ्रू आप प्रोजेक्ट ले सकते हैं, कॉन्फ्रेंस ऑर्गेनाइज करने के लिए एड ले सकते हैं। 4 रिसर्च बोर्ड हैं कि आपको ग्रांट लेने के लिए अगर प्रोजेक्ट लिखते हैं या कॉन्फ्रेंस ऑर्गेनाइजेशन करने के लिए एड लेना है तो आप डायरेक्टर ईआर एंड आईपीआर को कांटेक्ट कर सकते हैं। एट प्रेजेंट डायरेक्टर मेरे रोल मॉडल डॉक्टर शिव कुमार जी हैं, वो अभी रिटायर होने वाले हैं, उसके बाद नेक्स्ट डायरेक्टर आएंगे, उनको कांटेक्ट कर सकते हैं। और रिसर्च बोर्ड में अगर कुछ आपका काम है लाइफ साइंस, आर्मामेंट, नेवल रिसर्च बोर्ड या TRNDB से अगर प्रोजेक्ट लेना चाहते हैं तो उनके मेंबर सेक्रेटरी को कॉल कर सकते हैं, बात अपना आवेदन भेज सकते हैं। जो फॉर्म रिक्वायर्ड है वेबसाइट में वर्ड डॉक्यूमेंट में अवेलेबल है, आप फिल करिए, भरिए और भेज दीजिए। मेरे से कांटेक्ट करने की, मैं बहुत छोटा आदमी हूँ, मेरे से कांटेक्ट करने की भी जरूरत नहीं। नेक्स्ट, जो बच्चे आपके अंदर में पढ़ने आते हैं, ट्रेनिंग करते हैं, DRDO जिस फील्ड में है पूरा आपको चार्ट दिखा दिया गया वेबसाइट में, सारा अवेलेबल है। अगर आप उनको ट्रेनिंग कराना चाहते हैं प्लीज सिलेक्ट करिए, डायरेक्टर को लिखिए, आपके कॉलेज का डायरेक्टर को एड्रेस करते हुए एक लेटर लिखिए, एक बायोडेटा लगाइए, बच्चे का ईमेल एड्रेस लिखिए, आपको डायरेक्टर को एड्रेस करिए, आपको ऑफर लेटर तुरंत मिल जाएगा। 15 दिन से लेकर के 6 महीने तक की ट्रेनिंग मिलती है। नेक्स्ट, थैंक्स, मैं क्लब काम कर। नेक्स्ट, आज मैं मेरे परिवार के कारण यहाँ, परिवार मेरा साथ दे रहा है, धन्यवाद।
I request Professor Choksi to come on the stage and request the organizer to present a memento as a regard to sir.
देखिए ना, तो मैं डॉक्टर हूँ ना प्रोफेसर हूँ।
Okay.
ये मैं अपने सारे डायरेक्टरों को जाकर के दूंगा।
For the next talk of the session, I request Dr. Gopi Chand Kaple from TU Nepal to come on the stage. So I request Amita to please quickly introduce the speaker of the session.
We have here today Professor Gopi Chandra Kapri. He is a Central Department of Physics, Tirubhavar University, Kritipur, Kathmandu, Nepal. He is going to speak before us on the topic AV initial investigation of structural and electronic magnetic and strain effects of selected crystal alloys. Welcome, sir.
Okay, thank you. Thank you to the organizer, especially Arvind Srivastava and the organizing committee. Today I am going to discuss about any initial investigation of structural, electronic, and strategic of the substrate useful place. I am going to talk about the three types of relay in MNCST and the other particles. We have the one poster by Ramba Rai in the poster session as well. This is my lab, CDP lab view. This is my Pure University. I have only the limited resources, only 5 computers. I have to work within this limited resource. And the name of that lab is Vector Science and Computational Nanomaterials. This is my collaborators group. Anurag Srivastava is also one of my collaborators. Right now we are one completing and one we are working in water splitting. And I have the water request from and the model from EMS lab, and I direct this from the University of Patras, Greece, and here model with him we are working in water splitting as well. Actually, what we are working in our lab is we are doing the nanostructure molecule clinics and GROMAX for the arsenic, lead, zinc, iron, rainbow using the nanotube nanosets. And the electronic and magnetic properties of the dot perovskites, perovskites, installatory, and binary types of alloys. And some of them we are also using in the 3D materials, 3D mixings, and trans 3D materials as well. Right now we are moving towards that water splitting, and two of my PhD students are working in trans 3D materials and others, and one is working in water splitting and only in this level. Today's talk is based on the above peoples, and the two students are actually completed from my lab PhD completed and other are working. Actually, today discussion we'll discuss outline of my today discussion is this. Today we'll actually going to discuss about the three types of slavery, especially in M3 as we. This strong one is strong results, and the part is there are STI, the J, Albany and India. Because it has the various kind of applications in the nanomaterials and semiconductor spin forest devices and the various metal spin forest devices, especially specialty devices. These are using both charge and spin both electrons, a new scheme of devices and electrons can means both both electron devices and electrons can be created because we can use high speed performance and the low power consumption devices we can make by these materials. So we are interested to work with it. Actually, because Eastern energy is generally used comes firstly discovered by the German engineering, CANDEE there. So its name becomes Eastern energy. First, there is just two widely types of Eastern energy. They have the different kind of properties, like this one. This one is metallic properties. This one is semi-conducting types of behavior. This is half metallic spin behavior. The one spin channel is conducting, and another spin channel which is slightly gap. And another kind of this is new type of sclerosis. Also, we can observe in the particle sclerosis and the sclerosis, which is gapless half metallic behavior. In upper spin channel, that is gapless, and in one spin channel, it is slightly gap. And while we are discussing about the magnetic properties, it has the various kind of ferromagnetic, paramagnetic, and various kind of magnetic behavior also we can observe within these materials. Actually, there are the various types of insular alloys. We can say the same insular alloys that is the XYZ, that is we can say half insular alloys, XYZ, and full insular alloys X2YZ. Quaternary steroids X2YZ, and inverse steroids X2YZ. In X2YZ and X2YZ, both full steroids, then X and Y can be interchanged. So there's one of them is the inverse steroid and another is steroid. Actually, and if X is equal to Y, and it turns out with the MN3 types of steroids, we can prepare these steroids by X selecting X and Y from the D metals and Z from the any one of them. And we can shift this to the we can use from the F electron elements, especially choosing ABCD sites and other Wyckoff coordinate sites, especially by using this technique. Atoms with higher numbers value they configure A and C sites especially. And with atom with a smaller number of valence electrons that occupy the D and D sites. And the main group elements generally occupy this aluminum and indium. These are main group elements. These occupy these sites. So we are using actually three types of alloys and the alloys generally crystalline into alloy to type structure and other partners to in three types of structure in general. And atom of X and X has more valence electrons occupy the sites 4A and 4B C sites. And atom with the less valence electrons, atoms that will Y occupy the sites 4C B sites, and on the main group they occupy the 4D sites. That occupation, same occupation rules occur means favors for all kind of structures. Generally, while looking for the density states and other electronic properties, we must go throughout the whether these are the stability or not. So while doing this theoretical approach, we are going to first structural stability, chemical stability, dynamical stability, and other types of mechanical stability as well. So we have done almost of the spiritual types of structure here by using the Y2K and the other quantum espresso and CSR. Whatever we means whatever we have, whatever we get a value, then we do that one. Okay, especially in the what happened, especially in the experimental equation in geothermal types of storage. MN3, yes, we was synthesized long years back previously. So synthesized by the reaction of elementary component under high temperature and pressure. It has a cubic level 2 structure. Structure PM3M structure with a 4 Armstrong diameter. Especially it is found with nuclear diffraction method use this M3 is the ferromagnetic ordering. But what happened if we are looking for it in the different structure, we get this LOT structure and slightly distorted LOT structure and M3 type, GO3 type structure. All three structures shows very clear kind of behaviors. All shows the ferromagnetic ordering are stable. Ferromagnetic ordering is stable, and we have chosen niche in the positions, SP positions, equivalent atom positions, and others MN position, MN SP, and the position of other MN and SP positions. Then this first is LOT type structure. Second one is distorted type of rectangular structure, and the third one is the GO3 type structure. And while we get the ferromagnetic ordering is the most stable one. Then actually why this will happen? The nuclear diffraction methods gives the ferromagnetic ordering, and other our calculation shows always shows the ferromagnetic ordering is the most stable one. So we got into actually we interested to work with it. Then we went towards this direction, and we make the supercell of 1 by 1 by 2 in the M3 SP. We choose the ABC in the antiferromagnetic 1, antiferromagnetic 2, antiferromagnetic 3, the spin up and down by giving this vision here in the interlayer up down up or down down, and interlayer in this means red arrow indicates the spin up and spin down of the Mn atom only, because Mn have the d electrons, so it has the magnetic moment as we do not have the magnetic moment, no magnetic moment. So we are using only d atoms, and this also actually shows the ferromagnetic. Ferromagnetic has the low energy with the magnetic moment 2.3 GeV per Mn atoms. Still, actually, what we are looking at is not matches with the nuclear diffraction experimental methods. So we discussed we use the spin orbit coupling in the different magnetic directions, and after looking the magnetic spin orbit coupling in the different magnetic directions, still we get the ferromagnetic order. Then we think why it is so happen. So there we use the unequal magnetic moment of the Mn atoms in different sides. So there we use actually where we transfer LNT structure at first. To do that, we transfer LNT structure to the P1 structure, and then use U. In our effective model in M1, we use the U effective as the 4 electron volt for the M1 side one, not on other M3 sides within this one. So yeah, after using this, we get the ferromagnetics with 3.97 MeV of the we get actually this result. We obtain this result is ferromagnetic ordering result. We obtain whatever given by the nuclear diffraction experiment. But from Ga plus U and Ga plus U plus associate, both after using this one, and we got M1 structure is the 4.1 magnetic moment, M11, and M12 and M3 as the magnetic moment minus 2.37. So it provides us the ferromagnetic behavior of the systems. Exactly, it matches with the this result of the X-ray diffraction result method, because it gives the ferromagnetic with 3.97 MeV and M1 and the 2.1 MeV for the M2 and M3 in opposite directions. So it matches with the results. And while we are while spin up and spin down, while looking for the spin up and spin downs, we got the some gap, direct gap within close to the Fermi levels. So it may close to the Fermi levels. Topological feature in K is the Fermi level in the between X and Y with high symmetric directions. While we are using the SOC, and these gaps are the more pronounced in this one. So only not I'm moving towards the topological features here, but we think that may be applicable for the topological one, and we are moving towards that also. We'll do it later on. Okay, then after we are actually using the different structural parameters of different, we are checking with the different structure, tetragonal ferromagnet, yellow ferromagnet, and we observe that this tetragonal ferromagnet is most prominent and most stable one, and which favors the Newton diffraction methods. So global minima of the tetragonal phase with another activity is minima, that is language structure phase transfer with very small volume change. So the first order phase transfer from ferromagnetic to ferromagnetic within the cubic structure with extra 12.24 mega energy, which is very small energy, and there's large energy difference between LN10, LN10 DO3, LN is here, and DO3 is LN is here. So that is used energy dissipation. It is the same within this table as well. That is the scenario in case of the useful array, and this means next parameter is matches with the experiment one electron structure calculation, and without spin coupling shows the topological material nature with the multiple features may shows that one. The calculator does suggest that there is appearance of the pseudo gap in the compounds. We got the pseudo gap of 0.23, something like that. And the ferromagnetic behavior of the magnetically non-equivalent amino atoms created by imposing the low symmetry structure, because that non-equivalent, we have to give the magnetic weight in the non-equivalent sides of the elements. So same initial dimension in the agreement with the Newton diffraction results. And aligned to magnetic phase with amity acid found more stable than that of giving DO3 phase. This is our result. And in quadrational elements, we use ZrRSTI Z. Z is aluminum and indium. It is similar to the ZR base quaternary alloys, and which is formed by the combination of ZR2 as Z and Ti2 as RS. Z types of behavior. Experimentally, ferromagnetic aftertalic is actually rare, so we are looking for the ferromagnetic aftertalic type of system. Which was observed in the thin film CO2 MNSI at the room temperature. We observed it. A similar experimental innovation has been performed in the CO2 MNZA, which gives the ferromagnetic behavior 80% spin horizon at the room temperature. And the same kind of behavior observed in the CO, FPCR3, and this also shows the half frequency with magnetic moment 3 MeV and 0.9 MeV respectively within the room temperature, within the room temperature. And this material CO, FPCRS, this in SIG, that observed the stable structure at the heat equipment. However, the magnetic moment means 2 MeV per formula unit and the 3 MeV per formula unit, which actually obeys the Slater Pauling rules very effectively. So by looking this one, that we are motivated to work within these materials, ZrRSTI. And we actually we use this white coordinate for the three systems. ZrRSTI, where Zr is the red one and RS is the brown one, and the blue one is Ti, and the other one is Z. And we observed that ferromagnetic behavior is more stable in both of the cases. Most of the cases, ferromagnetic is stable, is like the previous calculations. Formation question is both gets the negative one. We have also calculated the dynamical calculation, also dispersion reaction also shows the positive behavior, positive part. So we confirm that these materials can be stable and can be synthesized experimentally, and this outcome is close to the OKM database as well. So while looking at the external state plots, we have seen the very peculiar kind of behavior in both cases. In ZrRSTI in aluminum, spin off channel shows that is slightly gap. Spin channel off gap, and spin down channel. Spin off channel is red one, and spin down channel is blue one. Spin off channel shows the slight bend. Up channel shows the bend, and down channel shows conductive behavior. It's half-metallic behavior. Just opposite in case of ZrRSTI indium based these materials. And this half beta is actually realizing the opposite spin channels in both of the cases. And band gap will be within ZR RS TIL and ZR RS TIL 0.25, 2.207, 287 electron volt to this one from the GJ plus U and GJ plus, and we are using the MPJ as well because we have to try this with the experiment one. So after using it, we got this kind of situation. Means here this is the case of there are aluminum-based alloys, and this is the indium-based alloys. Is upper spin channel shows the half metal behavior, and here it shows the low spin channel is the half metal behavior. The major contribution of gas in the real of formula are due to strong big advance of there are 48 RS 48 TI 3D states. There are RS and TI 3D states and the strong the contribution strong big advance or and this vibration we got this kind of behavior here. And the 100% spin potential here the formula contribute either in the majority and majority spin channel is the indication of orbital property of this system. Same kind of behavior is obtained in case of GG plus U approach. We use U parameters 1 electron volt for the observed there are 2 electron volt for RS and 1.5 electron volt. It is by taking the base of experiment and then the trial and trial method we are using U. So and same kind of behavior is obtained in GJ plus with MBJ. MBJ also same kind of behavior. Actually, and the band gap actually follows the band gap division mechanism. Here, actually, in the single is 5 ZRRS bonding, 4D orbitals, T2D and TEGD. Under the 3D orbitals of the TI, and again from the bonding and anti-bonding bands, while the 5 non-bonding orbitals, 4D orbitals, T2 5 orbitals still remains on orbitals. Similarly, there are the allocation of 15D orbitals in the magnetic majority spin channels are these on, and there are arranged the high energy, lower energy channels here. Here, this is the 5 means 15 electrons. Actually, the main group Z will create the 1s orbitals and the 3p orbitals which are completely occupied, and are the below 15 averaging the d orbitals. The triple degeneracy states are not occupied with the both spin channels, and energy band gap is formed between this non-bonding and the bonding orbitals in the magnetic spin channels of the equivalent compounds. These are the calculations. Actually, this follows young Z demands 18 Polish exclusion. Slater Polish rules. Z demands 18 Slater Polish rules, and because we have in all in this case, the valence electrons upon the states are the 20 that calculated negative moments are 2 dB. They are indicating these systems follow these rules, and Q temperatures also we are using the different approach 2x3 cavity, 3x2 cavity, sorry, 3x2 cavity, and we get in both of the cases this type of Q temperature 450 Kelvin and 500 both Q temperatures exist. Means this indicates that these are the promising candidate for the spin tronics and the prevalent application, since applications. And another, while applying the after application of the strain, after application of the strain, a peculiar kind of behavior we observe. What happened? This is the zero stage. It's up spin channel as the gap, and down spin channel is as the down spin channel. After the application of +2 and strain, this spin flip, spin up change to the spin down, but it is not affected in the -2 state. On that side of the state, same kind of is occur when if there is no in case of another one there is no change in the positive state, but when -2 state it splits off. It flips actually that spin flips. It is maybe due to the effect of exchange interaction within the ZR and T. And same kind of situation observed in case of MBJ. This we are using the GJ technique, and we use this one MBJ technique. Well, follows this one or not? It also follows the MBJ technique, and GJ plus Q also follows the same kind of technique, same kind of behavior. So this results what the orbitals retains within the lattice parameters. This range within the distance 6.3 to 6.59 59 angstroms for this aluminum-based compound, and 6.51 to 6.78 angstrom for this indium-based compound. This phase inversion in the band gap from spin up to spin down channel has been found during the elongation and elongation of the equilibrium that is constant. The active density is retained up to 2%, equivalence parameter, and after density is no longer maintained beyond of that. But during the contraction, there is no phase inversion band gap, and the after density is no longer maintained on the other 2%. Similarly, this one indium-based compound, the phase inversion band gap from spin down to spin up can occur during the contraction of the equilibrium lattice constant or beyond 2%. However, there is no phase inversion during elongation of the after density maintained within 2 or beyond of it. The main reason for the phase inversion is the role played by the extended reaction generality and with aluminum and indium. In addition, the anomalous spin flip in -1 and 1 position is also found in these materials. And now, where is the magnetic moment with the lattice diameter? How magnetic moment varies with the lattice diameter? This shows that this 2 means up spin channel, means it goes up to 2, and the down spin channel also is going to. The result shows that magnetic is constant 2 may be in the both of the compounds. But appreciable change in atomic magnetic moments are still special and Ki rather than aluminum and indium in both of the cases. This is the spin channels. It means this interstellar and atomic charge along with the different magnetic moments are developed here. The total valence charge follows the quantum mechanics 2 rules. Then both composition with the opposite spin, opposite total 2 UV and magnetic moments. Especially this is aluminum compound follows 9 minus 11 minus 2 rule, and this one indium channels 11 minus 9 2 rules consider the separate up and down charge. Okay, so both of gives the same magnetic moment of this one. So these are the conclusions. This calculation for mission and question energy and other kinds of dynamical, especially dynamic energy, shows the stability of this. That development that is parameter for the compounds. These both of them are this one, which are close to the experiment one, and the Curie temperature of this compound or this room temperature. You get this compound provides and the first applications, and this compound are found to be the metallic nature with gap of this gap and this gap of and this one also this gap. From the all either GGA plus U and GGA exchange production functional of the magnetic property are mainly originated due to the average electron distribution such by this latter following 18 rule with 100% spin polarization. All three exchange production functionals support the same results. There is the phase inversion after the spin gap is spin up to spin down channel in this one, and spin down to spin up channel in this one after application of uniform state up to plus minus 2% of the equilibrium lattice constant. Shifting of the mixed spin channels found here could map to the exchange bias like big experiment offered in some of these right. Thank you for the CANDEE groups and
Thank you, Professor Kapli, for a wonderful talk. So, before I ask you the question, I have a small question.
Okay, sure.
I'm not a theoretician, so I'm just wondering about whenever the theory people are talking about, for example, the band gap value we are talking about. So 0.287 and 0.280, like, so it is up to the 3 decimal places.
Yeah.
So are you talking about that plus minus range under this, or
no,
it is like more accurate and like?
Actually, that plus minus range, I don't know about it. It is because of that within the computational accuracy, that will give the computational accuracy. But in general, we are using in the computational, we are using 10 to minus 6 electron volt and something like that. Means that range. Okay, so we are taking only 2 or 3 digits of the accuracy one.
As Rajiv mentioned in the modeling, actually, the absolute numbers doesn't have not much significance. The trend is important.
Yeah.
And also, what
It is a relativeness in the system.
what was her question is 287, 280. There is no error bar.
Yeah.
Those numbers, as he said,
Yeah,
2 minus 6 is used. So those numbers are absolute, but those numbers are not that meaningful as he was telling.
That is in the relative sense, those are not absolute. But whenever we are just comparing the data in that. So in the experiment, we are talking about that statistical range in plus minus up to the third decimal place, 2 decimal place. In the experiment, we are talking, and the people are asking to us also ki how much accurate results you are getting in the experiment. So I'm wondering about how much accurate is the theory also.
Actually, in the experimental theory, it follows the Slater-Pauling rule or not. Okay, experiment also follows that one, and our system also follows that one. That matters actually.
Like in any theoretical talk in numbers, did you ever see when the plot there is a error bar or a plus minus? No. That is because we are working in everyone a 6 range or 5 range something.
Yeah. Yes.
Any other questions from the audience? Yes.
How do you take the still urban coupling take into consideration in Vina calculation?
Pardon?
How do you take consideration?
Still urban coupling in
Vina
Y2K? Yeah, in Y2K. Now there is the permission. In Y2K there is separate permission. You can use the that you either in the east side of the, for example, compounds or any sides you can use. There is the permission. But selection of you is very difficult. Either you have to go throughout the linear response approach or you have to go the random approach. Spin orbit coupling. Yeah, in spin orbit, whatever you know, there is the process you can use. There is directly you can use the spin orbit coupling DR patterns. There has the going to get there has the provision of that. In every DFT program, there is the problem.
He's asking if there is a provision in Win2K or not.
Yeah, let's go.
In
It has
Win2K is not.
Sure.
How is it being done in Vina?
Okay, later on you can just
Okay.
carry the detailed discussion. Short discussion we can carry there. Okay. If there is no any other query, so it's time to honor the sir. It's my privilege. You give me and
Thank you so much, sir. I request Samar Bam to kindly announce the name of our oral presentator.
Now the session is going for the oral presentation of the day, and today we are having the first oral presentation from Dr. Ashwini Kumar from Awadh University, Ayodhya. So for the oral presentation, we are having total 10 minutes, 8 minutes for the presentation and 2 minutes for the discussion.
So very good afternoon to everyone. First of all, I wish to thank to the convener, Allah Swastika, and other organizing committee to include my talk for the presentation. Topic of my talk is structure and electronic properties of thin two-dimensional tungsten disulfide within simulation framework of quantum espresso software. So this is what I was learning and I was also doing. So I have some results. So this is the outline of my talk, which is divided into the following topics. First, I will introduce the problem. Then I will go to the density function theory, how it is beneficial and how it is being replaced to old quantum calculations. tungsten disulfide, why I am using this material, and then I will discuss about quantum software which is based on density functional theory. Then I will discuss some computation details, and so my preliminary results based on the tungsten disulfide. Mainly it is conversion study. Conversion study is respect to criterion cutoff, K points, like parameters, and another study is density of states, which I have done, and I will show that, and finally I will summarize my talk. So two-dimensional materials have been paid enough increasing amount of interest due to their unique potential applicable for wide variety of optoelectronic devices. The metal chalconite are among most effective 2D layered materials, and because they can avail us the atomic scale thickness and a significant band gap to replace bulk semiconductor and being used for photovoltaic applications. So this tungsten disulfide is a transition metal like chalcogenides and very important layered material and has potential to having suitable chemical and physical properties which are very crucial and beneficial for solar cell devices. So this is a little bit about tungsten disulfide. So tungsten disulfide is a metal like chalcogenides and have honeycomb hexagon lattice. It is strong tungsten, sulfur, and tungsten sulfur covalent bond between layer, while adjacent layers are held together by big bond of force. Its primitive unit cell have one tungsten atom and two sulfur atoms in a trigonal prismatic configuration. By appearance and feel, tungsten disulfide is similar to graphite, and most importantly, it is very robust under the mechanical strain. So overall, if you summarize, we can say that tungsten disulfide we should use because it has good electrical properties, good transport properties, it is transparent and flexible, and it is relatively inexpensive. That is quite important thing in material science. So materials consist of atoms and molecules. These atoms and molecules are having electrons and positive ions. So if we want to calculate the properties of a material, we have to solve Schrodinger equation. So this is quantum mechanics approach. And if you see, for a simple system, you have to write the Schrodinger equation in the form Hamiltonian consisting of many terms. This first term. So this first term is the kinetic energy of the electrons, and this second term comes from the kinetic energy of the ions, and positive ions. This third term comes from the interaction energy between electron and electron. This fourth term comes due to the interaction between ion and ions, and this one due to the interaction between electrons and the ions. So this equation maybe look simple, but when you will go to solve, this is exactly solvable for one particle system, like one particle or two particle system. Simple example is hydrogen atom, which is exactly solvable. But as the particles go on increasing, it is not possible to solve analytically. Even we can go for numerical calculations, but there are limitations. Because if we take a drop of water, just a single drop, 1 ml, you will find at least about 23 molecules are there. So we can guess how much electrons and ions, total number of particles get too much high. So quantum mechanical approach is very efficient approach, but analytically it can be not be solved, and numerically it also has some limitations. So density functional theory is very efficient and general, but implementation of approximate and hard to improve. So this many body interacting system, how can we deal with this DFT approach? It works like if this is an atom and this is positive ion nucleus and there are electrons surrounding it. So electrons and electrons are interacting with themselves. Electrons are also interacting with ions and ions are also interacting with themselves. So this is too much complicated. Many interesting terms arising in the Hamiltonian. But the DFT considers this interesting terms reduces into electron density terms and ion terms. So when we are discussing about electrons and ions, then we can see that electrons, mass of the electron is much lighter than mass of nucleus. Nucleus is quite heavy in comparison to electron. But in terms,
Sorry to interrupt you, 2 to 3 next to 1.
from here I can say that ions are neglected here due to their heavier mass and their slow motion. So they are treated as a rest and not taken account into the calculation. So I will come to my results. So based on these discussion and using quantum discussion, we have calculated convergence with respect to kinetic energy cutoff, convergence with respect to K point cutoff, convergence with respect to lattice parameters, and at last density of states. So here, the number of K points, with increasing number of K points, total energy of the atom is plotted. And we see that the energy initially start decreasing and after T, it is getting saturated. Straight curve. So we can see that it is not getting higher or lower value. So in between, any value can be chosen for the calculation. So in general, I have taken 6. Here with lattice parameter, here I am varying the length of the lattice parameter and the other side is the total energy of the atom. So we find that there is minima around minus 400 at 6. So this is the value I should go for the calculation. Now this is density of the density plot. So this curve is on x-axis is energy and on y-axis the density of states, that is spins. In summary, we have first we have optimized the structure of the convection disulfide by carrying out the X-Vision software. Another thing we performed convergence study with respect to kinetic energy performed, and then we performed convergence with respect to K point using SQL calculation, and then we performed convergence density of state study. And further, our goal is to calculate band structure by using NSQL. Thank you.
The talk is open for the discussion. If you have one or two. Yes.
In your DFT calculation, that lattice parameter you have taken,
Yes.
as it is 2D material, you have taken only the lattice
Only
parameter or A, B, C, both?
only one parameter. Other parameters I have not shown here because I know that limitation of time is here. So I didn't include those plots.
It's one sort of the work he presented here.
But all these 3 have been done, and once we go for more rigorous research, we will put all those together and then we finally find what is the minimum.
And quantum expression you have downloaded
This is open source package, so we can I have downloaded, and I have Linux based Ubuntu system 20, Ubuntu 20, and workstation I have 32 core. So yeah, this is so for the simpler structure it is very good.
Thank you, Dr. Ashmi. And moving towards the next oral presentation of today, I may invite Dr.
D.R. Paudel from TU Nepal for his presentation. So again, as a reminder, you have the 10 minutes. 8 plus 2.
Hello, good afternoon everyone. Myself Nasram Model and chemistry professor in Tirumala University, Nepal. And today I am going to talk the insight into electrocatalytic water splitting activity of the tungsten-based nanomaterial for green hydrogen production. Today in morning session we listened very good talk about green hydrogen and the possibility. And I am the experimental guy, that's why I didn't do too much theoretical work. But during publication, I did DFT calculation with collaborators from Japan and South Korea. These are the outlines of my talk today. I will discuss about the hydrogen evolution reaction, HER-OER, for the water splitting device and the application of the material in the zinc battery. As we know, already discussed this introduction part, very prominent professors already discussed about the use of green hydrogen to achieve the net zero emissions and the target for the world and hydrogen energy, why the hydrogen energy is emerging, and this kind of things are already discussed. So I don't want to spend the time here. So hydrogen fuel, we already know that it can be used in the various sectors like household purposes as well as the transportation and industrial sector. And this is also the prospective application, and the world is considering that hydrogen is projected to play a significant role in the worldwide industry in the near future. And these are some synthesis methods for hydrogen, green hydrogen synthesis, means hydrogen production as a fuel. And over here, the electrolysis is regarded as the best method or green method, which do not emit the carbon dioxide or any other gases into the atmosphere, which pollute the air and causes the greenhouse effect. So, water electrolysis using the renewable energy sources like wind energy or solar energy or hydro energy is our target. And this catalytic reaction, where water electrolysis occurs, electrolysis of reaction, we already read in very small classes, and the hydrogen and oxygen evolved in the respective electrode. And there are several kind of water splitting devices are there, but AEC is most prominent till date. These are the outlines of hydrogen evolution reaction and the oxygen evolution reaction during the water splitting process. I don't want to go detail for this. I will discuss the results of my findings. This is the ORR. It's very important reaction for the fuel cells, rechargeable metal air batteries, metal dissolution, and in the biological process also. Similarly, the zinc air battery, we already know that from the childhood, zinc air battery is very common and it is the environment-friendly energy storage device, and it has a very simple battery setup as the reaction chemistry. We designed electrocatalyst by being a chemist. I just focus the transition metal and tungsten is my main motive because of its copious natural reserve and versatility in the oxidation state. You can see that many oxidation states, electronic states can form for tungsten, and it can coordinate with many kind of things. And our strategy mainly relevant to the cation ion doping in the tungsten disulfide, as well as we made 2D heterostacking with the nickel telluride and the tungsten sulfide, and later on we prepare heterostructure of tungsten oxide with tungsten carbide and the MOF, which is regarded as the functional composite as an organic inorganic. This is our strategy. How the electrocatalytic activity can be enhanced is by making the functional composite, where we prepare the WO3, tungsten trioxide, by very simple hydrothermal method, and the pseudomorphic transformation by the annealing process in presence of iron. The tungsten oxide is partially converted into the tungsten carbide, and the heterostructure is formed, WO3 and WC. And then we hybridize the WO3 WC with the organic groups because of the porosity. They have very high porosity morph ligand, and we use the BTC as a morphing agent. And this figure shows the synthetic procedure. This is the results. Maybe many are here from the physics background. That's why means this one might be more interesting for you. This is the XRD. We all know that, and the formation of the composite is here. And next figure shows the XPS for the electronic states, and we did the BET for the pore size and the surface area of the catalyst. Similarly, this is the FESM and TM analysis. We did FESM analysis for the different sample W3, W3, WC, and the formation of the dendritic structure of the composite material. And it has been found that the dendritic structure has very good catalytic property. And this is the tail images for W3 and W3, WC, and the composite material with the SPM image also, and the electron mapping is also there. Come to the electrocatalytic property. First, we analyze the oxygen catalysis by OER, oxygen evolution reaction, and the ORR study. It shows, as the result shows, very good potential, half-life potential for the ORR study with 0.81 volt, and which is near to 1. And its definite slope is very low. Its reaction kinetics is relatively high, and it follows the electron transfer process with 3.89, and the theoretical value is 4. And the 20,000 cycle of chronoamperimetric stability analysis, so the 94.9% retention of the molecule, composite molecule. And similarly for the OER study, we found very low overpotential around 249 millivolt and 10 milliampere per cm square, and the TEFL slope. So we also did the stability analysis in different current density like 10, 50, and 100 milliampere per cm square, and the figure shows in figure J, so the good stability direction. And we did the bifunctional catalytic activity by plotting the OER versus ORR plot. Similarly, for zinc, if the catalyst show the good OER and ORR activity, we can check for zinc battery, and the zinc battery property with 0.659 volt over potential difference. That's why we check by different methodology, and it shows the over the circuit potential at about 1.435 volt. And this is the hydrogen evolution reaction and the cell setup for the water electrolyzer. And we set up the cell for the water electrolysis reaction where the cell potential is around 1.53 at 10 and 1.83 at 100 milliampere per cm square. And this stability for 48 hours of CA. We did very small DFT calculation, and here the density state is calculated where our composite catalyst shows the very good total density state at Fermi level. I just want to skip this because this work is also published in Nanoenergy in 2022 issue. And here we make the heterostructure of 1T COWS2 with nickel telluride as a framework. And here we see the heterostacking of 2D material, and it shows a very good electrocatalytic property. And we check for the HER, OER, and ORR application. And these are the efficient image and other characterization tools. And this is the HER and OER reaction where the cell potential is very low, around 1.53. And mechanical study by DFT. This work was done by our collaborator from the Japan, Osaka University. And he calculated the battery charge analysis around 0.81, and the free energy calculation is around 0.01 electron volt, which is very good catalytic behavior. And this one is also published in the Applied Capacity Environmental in 2021 issue. These are the results. And I just want to focus today that so many dignitaries are here, and we are from the Nepal. And as you know, that Nepal has very high resources of water and clean water from the mountains and everywhere. That's why there is very high possibility of hydropower energy, which is clean energy, and we can assemble the hydropower energy with the hydrogen production channel. And already one Indian company make collaboration for the production of hydrogen, and they connect the plant here. and we have found a new collaborator for the assembling of that hydrogen energy, means hydropower energy to produce the hydrogen gas. And Nepal's green hydrogen potential is, as you know, we have at least 10,000 megawatts of hydropower by 2030, and with a demand of approximately 7,000 megawatts. So surplus energy is there around 3,000 megawatts, so that we can produce a large amount of hydrogen, green hydrogen, by using this. And the Investment Board of Nepal already calculated that we can produce the hydrogen in the uptime of from the hydropower energy with below $1 per kg. These are my conclusion, and this is my research group and our contribution. Some papers from our group, and this is me and our research collaborator. I want to acknowledge Professor Anurag Srivastav. He is also a collaborator with us, and Professor Gopchandra Kafle, and other professors from South Korea and other places. I would like to acknowledge my supervisor, Professor Jungmi Lee of the Dongbuk National University, University, and CANDEE 2023 team. And this is the line. The combustion of fossil fuel currently produces 83% of global carbon emission. Those are, let's invest in our planet, go green, and net zero emission. Thank you, and Dhaniyawad.
For a wonderful talk and a very fine talk, I must say. Talk is open for the discussion. Yes.
In one of your slides, you have reported one of data GS something.
Yeah.
What it refers? What is the significance of that?
Kelvin zero means reaction is very spontaneous. Its catalytic activity is relatively high. So the value is near about the zero. It means the high catalytic property.
So I have one query that you are testing this catalytic properties in what kind of the pH? Alkaline, basic, or
Alkaline, yeah.
in
All in all.
Sir.
You have shown the PET for your composite.
Yeah.
Is it the mesoporous or microporous?
This is mesoporous. Yeah.
So, okay, moving towards the next. Thank you.
Thank you.
So, I invite the next speaker of for the oral presentation, Dr. S.P. Singh from the Awadh University. Present here?
Yes.
I was looking there.
Very good afternoon, honorable session chair, the expert member, and dear attendee. I am Sabran Khan, assistant professor, Awadh University. I am also a research scholar, part-time, from M Gorakhpur. I am going to talk on topic electricity generation by motion of vehicles on highway and its utilization in EV charging. I think this is the first topic belonging to energy. Before going to start this presentation, I want to share why I have chosen this topic for presentation. You know, today everyone talking about sustainable development, GHG emissions, and global warming, GHG reduction, etc. And to reduce the GHG emissions, there is only way. We have to use all the energy which should be produced from the renewable energy sources. And the most reliable and easy to use renewable energy resources, that is wind and solar. But you know, the efficiency of the wind and solar, that is very less. The efficiency of the solar, that is lies between 25% to 35%. And the efficiency of the wind turbine, that is lies between 20% to 40%. Then is it suitable to tackle the energy demand of the future when your large amount of EV load will appear in future, next 10 years, next 15 years? Then as an engineer, I have thought, why should not we hybridize the two renewable energy resources like solar and wind? That's why I proposed the solar wind tower, which I will discuss in next slide. These are the outlines of the my presentation. First of all, introduction. As you know that advances in non-conventional energy technology and increasing fossil fuel prices, along with the environmental concern, have made hybrid renewable energy systems important. In view of this scenario, solar panel mounted on the wind turbine, called as solar wind, can be utilized to produce more energy than individual one. This solar tower will be located in the space available between the two opposite roads of the expressways or highways. As you know that these solar and wind are normally existed where wind are normally utilized in the coastal area, where the flow of wind there should be no hindrance, and solar where we utilize this where the sunlight available in abundant. And solar wind tower located in such a manner that the velocity produced from the driving vehicles on both sides on the road and equipped to cut the turbine blades in order to operate the blades. And next, energy generated from these solar wind turbine, it will be stored in the battery energy storage system, and it will be again distributed as per the requirement, either to charge the electric vehicles or either to feed into grid. Motivations for this work: climate change is a big concern for everyone. Fossil fuels release a significant amount of the greenhouse gases and heat that surround the earth and trap solar radiations. Almost 90% of the carbon dioxide and 75% of the greenhouse gas emissions producing from fossil fuels, which are the biggest reason of the climate change in the world. India has also set the target of 50% GHG emission reduction by 2030 and reach 0% by 2070 in order to prevent the climate change. Then we can see that is the Paris Climate Summit. There are 3 goals for the India, which has been said. First one is a target of net zero emission by 2070. Goal second, emission intensity by the GDP to reduce by 45% by 2030 with reference to the 2005. And third goal is to keep average temperature below 2 degrees centigrade. And all these 3 goals will be achieved by when non-fossil fuel electric installed capacity must be reached 500 gigawatt, which is currently only 176.49 gigawatt. Then we have to change this target, and it is possible only when we will produce more and more energy from renewable energy resources, and which will be get by hybridization of the energy renewable energy resources. Methodology. This is the block diagram of the solar wind tower. Here, this is DS type vertical axis wind turbine. DS there is 7 years wind turbine. which it make it self starting. And second module, this is the solar module. This is the wind turbine, and energy produced will be fed into the intelligent controller, and which will again it will fed to the battery energy storage. And according to the load requirement, it will fed to either directly to DC load or AC load, and AC load will be fed through inverter. And intelligent controller will decide where it will be fed, either to grid or the local load. And this is the physical model. As we can see, this is the high edge, and from one side, this is the another side. There is space. We have seen there are available space 2 to 5 meters along the expressway or highways, and where we can set up solar wind tower. These are the one solar wind tower. These are the second one, and it can produce energy, and it can feed the charging station. We can establish charging station along the highways, and this energy can be fed locally to locally established EVCS. EVCS means electric vehicle charging station. And okay, I have finished within time. Vertical axis wind turbine. We are using a vertical axis wind turbine rather than horizontal axis wind turbine because it's cover less space, because space available between the roads that is very less. And we know that this is the torque mechanics or force mechanics on the horizontal axis wind turbine, where upper half azimuth, upper half of the parts gets larger velocity than lower half, due to which it gets rotating. And in the case of the solar wind tower, the wind flows due to the motion of the vehicles running on the expressway. In this case, the unidirectional torque will be produced because the winds flowing in opposite direction, due to which it will produce the unidirectional torque on the wind turbine. This is the flow chart of the work. In this flow chart, we can see that we have used the intelligent converter, which will decide where our generated power will be fed. When SOC state of charge, we can say how much battery has stored the power. If state of charge is greater than 60%, then if yes, then it will supply to grid. Means we have sufficient amount of energy to feed the grid. And if we have less number of less than 60% SOC, then it will feed to the local loads or local EVCS, electric vehicle charging stations. And in such, we have used the Zephyrus wind meter, a digital tool. It can be installed in mobiles. It looks like this one, and it provides the velocity data. When vehicles will move on the highways, expressway, we have measured how much wind will be generated from the moving vehicles using this app, the Zephyrus wind meter. And this is the table. This is the table for the data. We have got with help of the Zephyrus wind meter, and this is the speed of the vehicles. This is car, bus, trucks. We can see in this table, car when running at a speed 52.9 km per hour, it will produce the meter. When I will convert it in meter per second. Second one is meter per second, and last one is the wind generated from the that moving speed at that speed. Wind generated, and we can see car since space of the frontal area of the car is less, and its high speed produces less wind speed, while bus and trucks less speed will produce high speed of the wind because its frontal area of the truck is high. This is we have simulated this one on a Simulink model MATLAB, and this is the output of the voltage, current, and power corresponding to irradiance. This is the solar module of the model at the Simulink. This is the Simulink model of the wind turbine. This is the output voltage, current, and power corresponding to different wind speed. We have used permanent magnet synchronous machine. It is in power generation increases at higher wind speed from the graph. You can see that. And this is the hybrid model in which I have merged the both solar module and the wind module. And finally, power will be stored in this battery storage system, and again distributed. It will be decided by the intelligent converter. And this is the graph corresponding to overall power. And this is a short video. You can imagine what is actually it will happen after when we will model in physical mode. It will play. Below side, that is a wind turbine, and upper portion having solar panels, and the wind turbine will be driven by the wind speed produced by the vehicles. And this is the conclusion. We have taken the solar installation considered from 10 hours from 7 a.m. to 5 p.m. And from simulation result, we have seen almost 15 to 20 kilowatt hour can be produced from this solar wind tower in a day. And this range may be varied according to vehicle speed and day condition. And in as a conclusion, we can take a 40 kilowatt EV capacity can be charged from only two solar wind tower. And in other words, we can say saving energy is also producing energy. Thank you. These are the references, and thank you for doing business. Any further questions?
So what about trains, like bigger vehicle trains?
Yeah, it will be better.
Very small.
Yeah, it will be more better than express train. And I am trying to getting data from the train speed.
So you have proposed the model
Yeah,
for the India.
yeah.
It's not been in working.
Actually, before today, I have attended the EV conclave at BHU, where experts come from the MNRE, Assistant Director of MNRE, Ministry of New and Renewable Energy. I have discussed with them. He has told me just find out something solid and come to me for the project.
Idea is really good, but one has to be workable corresponding to the concept, towards
Exactly.
the material, for the proper installation and repairing mode also.
Exactly. Aerodynamic designing are also.
Designing. Yes, sir. Yes.
You have shown one table, right?
Yeah.
And in that, for the car, you have shown different speed.
Yeah.
Is
Yeah.
it a similar kind of car or a different kind of?
Different kind of car. Random. Not similar cars. At random, whichever is vehicle system is, we have recorded.
No, the serial number you have shown. No? That is number of trials or number of vehicles?
Number of trials.
Number of trials for same vehicle or number of trials for
Different vehicles. Yeah.
Yes. The idea is right, but it is already available. But the problem is that the integration.
Exactly.
For the solar and wind. Anyway,
It is there
all
in
the best.
Oxford also, it is there in Turkey that.
Yeah, very correct.
It is well known concept being already implied there. Yeah.
Yes.
How much the cost is proposed when it will come into reality?
How much?
Cost.
How much cost is proposed for this model if it comes?
For one wind
Okay.
solar turbine, say.
Actually,
Because whenever it is going in the employment stage corresponding to the to employ at any stage.
This work is currently on research level.
It is the concept idea is proposing right.
I have submitted this on MATLAB Evelyn, but you are asking about cost.
Because
I
to
was,
employ it, you need to work on the pilot scaling of that.
Exactly.
Yes.
Yes.
I wanted to ask that the intelligent controller that you are telling, but you are having two power sources, that is solar and wind. So will the intelligent controller take care of both the power sources also, or it will only take care of when it has to charge or discharge? Means it has to charge the grid, or it has to supply to the system?
It will take both the input, both the power input generated from the solar and wind, and it will decide what is the SOC, current SOC of the battery energy storage system. And when it will greater than 60%, it will disperse power to the grid. It will fed to the grid. If less than 60% SOC, state of charge, then it will feed or supply to the local loads or electric vehicle charging station, which is the most priority of the all sector.
The input for both the system, that is wind and the solar, they are different.
Yeah.
So at different rate they will be charged also. So I just wanted to know if the input side is also controlled or not.
Yeah, there is for taking input, there will be different intelligent controller, and it will sum up and fed to the master controller. Okay, that will decide. Yes.
Your electric vehicle, when it is giving the energy to the load and the simultaneously in the grid, that grid is yours DC grid or AC grid?
Grid is obviously AC grid.
No, there is some DC grid
Yeah.
also available now and we can have it. And how much voltage is required for charging the vehicle? Because your vehicle battery is important here.
EV charging.
EV charging.
Yeah.
Electric vehicle charging.
Yes.
What is the capacity of the electric vehicle battery? You are charging the battery of the electric vehicle.
Yes.
Then what is the capacity and in which rate they will be charging?
For charging electric vehicles.
Yes.
Actually, there is not a specific battery capacity in market. There are different vehicles, different companies, even same company are having different capacity of the battery. Our target is only to charge or deliver or supply the power storage which is stored at battery energy storage system, and which will be dispersed or supplied to the any load. That may be our DC or AC or electric vehicles charging station, or it may be also street lights, road lights along the expressway or highway.
Actually, we have designed one small system.
Okay.
What we know that we have tested the vehicle's battery also. Mostly they are 48 volt.
Okay.
And their ampere rate also from Mahindra and others. What we have investigated that it is almost minimum kind of 40 to 60 ampere. So ampere per hour.
Okay.
So in that case we have designed, and it is a low power dependent, 12 volt sometimes.
Okay.
In 4 battery in 12 volt form. So in series. So ultimately 48 volt is required.
Okay.
So we have designed a small DC bus or grid to actually power the mobile and the electronic system, especially in computer also. Low voltage DC grid we have designed so that maximum capacity to be utilized. So that is why I am asking that if there is any collaboration kind of thing to.
Sure. I will contact you after the discussion.
This one last query.
Yes, the problem is the reaction time is quite small.
Reaction time?
The car is passing by through your head and the reaction time is quite small. So, in meantime, the battery will be charged. That was saying.
No. In this duration, energy will be generated from the wind turbine, and that will be stored first in the battery energy storage system. Then after storing, after storing, it will be dispersed, not directly. Yes.
Okay, thank you for the detailed discussions we are having in this particular presentation. So today's this session is over and everyone is invited for the lunch.
Everyone can proceed for the lunch and we will meet again here after 1 hour, after half an hour. 2 o'clock.
It's not 2 exactly. Okay, it's discussion was 2:30 will. Exactly the one in between.
नहीं बंद है
I get a kind of it goes like that. New RIT is built separately, but earlier the they are part of this one, and later on they will convert it to some regional sectors and more. To work and you need to like divert the concept to the real. Yeah, it is.